Welcome back to another video by Firestarter Graphics and Engineering. Today we're going to talk about problem chapter 12.89 from Beer Vector Mechanics for Engineers, Dynamics, 10th edition. This problem is very difficult but very awesome and amazing. I don't know, it's just one of those problems that actually makes sense because it's so applicable to engineering, especially aerospace engineering and space dynamics. So the question is, we have a space shuttle S, which is over here, and it's in a circular orbit. And in order for the shuttle to receive a satellite or recover a satellite, it first has to be placed into an elliptical path BC by increasing its speed by a change of velocity in 280 feet per second. As it passes through B, it's hitting 280 feet per second. As the shuttle approaches C, its speed is increased by another 260 feet per second. So, to insert it into a second elliptical transfer orbit from C to D. Okay. Knowing that the distance from O to C is 4,289 miles, determine the amount by which the speed of the shuttle should be increased as it approaches point D to insert it into the circular orbit of the satellite. Okay, a lot of information. So let's get going. Okay. So this problem might take a few minutes, but I think we can get it. So the first thing that we need to do is we're going to draw a really big picture of what we've got going on here. So let's go ahead and draw what we have. We've got the Earth. Okay. I went ahead and just drew what we have. We've got the Earth. We've got our point B, point C, point D, our space shuttle, and this radius right here between the Earth and here is 180 miles. Okay. Okay, what do we know? We know that the change from velocity B is equal to 280 feet per second. Change from V to C, not V to C, change of velocity at point C is 260 feet per second again. We know that the radius from O to C is equal to 4,289 miles. In case we need it, the mass of Earth is a very large number, 5.9 e to the 24 kilograms. The radius of Earth is equal to 3,960 miles. Now, I don't know if we're going to need this. And the point from... Oh, the gravitational constant. Sorry, I saw GC and I was like, what the heck? Gravitational constant, 66.7 e negative 12 meters cubed, kilograms second. We may or may not need that. Okay. So, our job is to find the change in velocity at point D. Okay, so let's start. First thing we always do, we're looking at the space shuttle. We need to draw a free body diagram. So the sum of the forces is equal to the mass times the acceleration. But let me ask you this. Okay, so let me ask you this question. What acceleration are we dealing with here with the space shuttle? because we know that force is equal to mass times acceleration, but if the space shuttle is just sitting there with constant velocity in this orbit, then a lot of people think that acceleration is zero. That may be true. The space shuttle is not accelerating at all. But there is one thing that is happening, and it's called normal acceleration, because what kind of path is an orbit? It's a circular path. So that means we have mass times the acceleration of normal on this side, on the right hand side. On the left, the only force acting on this spaceship is the force of gravity. So for a circular orbit, we have the sum of the forces is equal to the mass times the normal acceleration. So, what do we know about the force of gravity? Let's kind of look at something real quick. We know that force is equal to mass times v squared over r. Okay. And in space, this comes from another derivation of just the normal of the definition of a normal acceleration along a circular path. Your velocity squared divided by its radius, or rho, if you want to call it that. So, in space, Fg is equal to g, mass of the Earth, mass of the spaceship, all divided by the radius squared. Okay, so what is this? Okay, that's great. So we know that we have Fg is equal to man. Okay, we're kind of going in circles here. There's not a lot to work with, so we need to start looking at some other things here. Okay, so let's kind of take a peek at our picture here. If this is B, where the change of velocity happens is at B, there's 2 points. We've got a minus and a plus. And we can say that with all of these, a plus and a minus, where we're looking at the velocity before and after each of these points. So we're going to call that VB minus and VB plus. That's kind of our notation. So we know B minus is where velocity was constant, and B plus is where the boosters are on and you're changing your velocity. So let's just kind of do some things here. We've got the gravitational constant, not F, times the mass of the Earth times the mass of the spaceship, all divided by radius squared. Now this is equal to mass of the spaceship times your velocity squared all over r. So our goal is to solve for at least this velocity. That's kind of where we want to see our velocity. Now we're gonna, so let's at least look at that, because we know we're solving for velocity. So if we get rid of the r, divide by m of the spaceship. Okay, we're literally just left with the gravitational constant times mass of the Earth over r is equal to v squared. So v is equal to the square root of gme over r. Okay, so now this v, what v is this? Well, we're kind of wanting to look at it where the velocity was constant, because if you think about it, what is a change of velocity? We know that the change of velocity at B has to be equal to, okay, the velocity at B minus plus the change of, actually, I have that backwards. Well, it's not really backwards. I hate writing it that way. So let's do it this way. We know that the velocity after the boosters are on has to equal the velocity of B minus plus our change in velocity right at point B. Because remember, this is right at point B. Point B. And this is before. And this is after. Okay. So, we know this one. We don't know this one. But we technically can find this one by right here. So, let's go ahead and do that. So we've got VB minus is equal to the square root of 66.73 e to the negative 12 multiplied by the mass of the Earth, all divided by the radius. Now RB, where is RB? I didn't check that out. It's 180, right? No. It's not 180. Radius of B, this is 180, but we've got to include this. So RB is equal to 3,960, which is the radius of the Earth, plus the 180 miles. So, oh man. Okay, our units are going to be crazy here. So, what is G in by chance? Mass of the Earth is in kilograms. Let's see. We're in miles. Kilograms needs to work with meters. So we've got to convert miles to meters. Okay, so we have 3,960 plus 180 multiplied by 5,280 feet per 1 mile, times that by 0.3 meters per foot. So miles will cancel out with miles there, feet, left with meters. And when we're done, that gives us a very large, well, it's not large, just a number. I'm just going to write that here. And when we compute that, I'm not going to do all the calculations here. We get that VB minus is equal to 7.73 e to the 3 meters. Okay? Now, that's our time, is per second on this. I don't know if you guys understand how fast that is, but that's fast. Okay? This is really fast. It's almost 5 miles per second. So, now that we know VB minus, we can go ahead and we know that we can find VB plus. So VB plus is equal to our 7.73 meter E3 plus 85.4 meters per second for the change of velocity at B, and that's our answer. So, really, really fast. Now, I want to talk about what happens. You're going to use this exact same approach for the other problems. There's only one difference. We have to deal with, since we're dealing with, okay, not that one. Since we're dealing with a circular orbit right here, and it's going through, there's one concept that happens when you deal with circular orbits, and that is something called angular momentum. This means there is no change of torque on a rotating object when it's conserved. So when angular momentum is conserved, there's no change of quote-unquote torque on the rotating object. Best way I can explain it in English terms. Angular momentum does not change, but because the spaceship is accelerating out of its current orbit, angular momentum is changing. When it's constant, there's no change of angular momentum. It's conserved, so there's no additional torques or rotations on that spaceship. But as we increase our acceleration, or our velocity, and therefore our acceleration is, the spaceship is accelerating, our angular momentum is now beginning to change. So let's look at this concept real quick. So, okay, we know that angular momentum is constant from BC to CD. Do we agree with that? Let's look. So from here and then there, yes. So angular momentum is conserved from here, but it's a constant change from there to there, from there to there. Okay. That's what we're claiming. So, with that in mind, we have RB plus multiplied by the mass of the spaceship times VB plus, because what is momentum? Mass times velocity. Angular momentum is radius times momentum. Okay, this is equal to RC minus multiplied by mass of the ship, velocity at C minus. So mass of the ships will actually divide out, leaving us with RB plus VB plus is equal to RC minus VC minus. Okay, we know this one, we know that one, and we know this one. So we can solve for this one. Okay, so let's go ahead and do that. VC minus is equal to RB plus multiplied by VB plus, all divided by RC minus, which VC minus, the velocity at C minus, is equal to 7.54 e to the 3 meters per second. When you plug everything in, that means with CD, it's from C to D, it's the same concept. The mass of the spaceship cancels out, so we have RC plus multiplied by VC plus is equal to RD minus times VD minus. Okay, so VD minus, when we solve it, is equal to 7.52 E3 meters per second. Now, VD minus is equal to VD plus change of VD. We know this, but we don't know that or that. So what do we need to do? Well, we need to do the exact same thing we did for point B, But for point D, mass of the Earth, mass of the ship, the radius of D is now equal to mass of the ship, VD plus squared RD. Because we don't know VD plus. But through magic hat operations, we get that VD plus is equal to the square root of GME over RD, which yields this 7.55 E3 meters per second. From there, take this answer, plug it into here, and then we can solve for VD plus. And then we're done. So, very interesting problem. I hope that helped. It's one of my favorite problems. It's a lot of fun to do. So anyways, as usual, thank you. And I hope you guys have a great day. And once again, I'm just a dynamic student, just showing my homework and how to do these so that other people can get the help they want.